Hi, everybody, and thank you for joining us today for this webinar about using climate data in the real world. I'm Ashley Lawson, a senior fellow here at C2ES, and I'm very excited about this topic and the interest you've all shown by being with us here today to talk about climate data. We had over 200 people register for this webinar, so we know there's a lot of interest in the topic. And I do want to get you right to the information you're here to listen to, but first, just a few housekeeping items. This webinar is being recorded, and we'll post the recording to our website at c2es.org in a day or two. We'll also take questions at the end, but you can enter your question into the queue at any time during the presentation. Please just use the question box in the GoToWebinar interface. I'll try to raise any clarifying questions that come up during the presentations, but we'll save most of the questions for the end. So while we're waiting for the next slide to come up, I'll just review the agenda for today. So we are going to be starting with some introductions and then hearing from federal scientists who are going to teach us some of the basics about what climate data is available to the public, how climate models work, and how they get downscaled. Then we'll get a perspective from the energy sector about how this data actually influences business decisions in the real world. And we do hope to have a lot of time at the end for Q&A, so please don't be shy about entering those questions into the box in the interface there. Let me introduce you to the terrific speakers that we have here with us today. First is Ellen McCray. Ellen is the NOAA Regional Climate Services Director for the Eastern Region. She helps bring NOAA's climate information to other federal agencies, as well as regional, state, and local geographies, and specific sectors of importance to the Eastern Region. She currently works with the transportation, coastal, public health, marine fisheries, and energy sectors. She is currently serving as the federal convening lead author for the 4th National Climate Assessment for the Northeast chapter, and an author on the Energy National chapter. And she has published work in a number of research journals as well. Next today, we're going to hear from Dr. Thomas Wall. Tom leads Argonne's Climate Impact Data and Decision Support effort, which aims to leverage Argonne's deep capabilities in climate science and modeling, advanced computing, infrastructure risk analysis, and decision science to provide actionable climate impact information to the engineering and planning communities, also to industry and to state and local governments. He has extensive experience in the area of critical infrastructure analysis and protection. We'll also hear from Dr. Feng. Yen is an atmospheric and climate scientist in the Environmental Science Division, also at Argonne, and a fellow with the Computation Institute at the University of Chicago. Her research examines improving the accuracy of climate change predictions by both global and regional climate models. She is also interested in modeling the global life cycle of atmospheric particles such as dust, soot, and sulfate, and also their impact on climate and environment. And last, but certainly not least, we'll hear today from Brian D'Agostino. Brian is the Meteorology Program Manager in Emergency Management for the utility San Diego Gas and Electric. As Program Manager, he provides operations support for the delivery of safe and reliable energy. He oversaw the design and construction of SDG&E's weather network, which is one of the most sophisticated and extensive weather networks in the country. He is currently serving as an advisor and former chair of the American Meteorological Society's National Energy Committee, and he works closely within the meteorological community to coordinate research projects specializing in fire science, solar forecasting, climate adaptation, and emergency management. Let me also briefly introduce C2ES for those of you who may be joining us for the first time. The Center for Climate and Energy Solutions is an independent and nonpartisan nonprofit organization focused on strong policy and action to address climate change. Our core mission is to forge practical solutions to reduce greenhouse gas emissions, promote clean energy, and strengthen resilience to climate impacts. We do this by bringing together city, state, and national policymakers, along with businesses and other key stakeholders. We have a group of businesses that we work most closely with as part of our Business Environmental Leadership Council. We try to learn from these companies what types of policies work in their sectors, and we hope they learn a little from us as well. This is the largest US-based group of companies devoted solely to addressing climate change, and I would encourage you to visit our website to learn about the BELC and what its companies are doing. Let me also acknowledge the funders of today's event. This event is part of our Solutions Forum program of activities at C2AS. It's an effort we've convened the last several years to work on solutions to climate and energy challenges. So thanks to Bank of America, the Energy Foundation, and the JPB Foundation for supporting this work. As one final point of introduction, let me just say that one of the key challenges we work on in our Solutions Forum is improving climate resilience in both the public and private sector. We know that having credible, up-to-date data on climate impacts is a key component of any resilience planning. The extreme events that we've seen so far this year have only increased awareness in the need to understand how our climate is changing. So the images you see here are showing wildfire, floods, and hurricanes, some of those really dramatic and acute shocks of climate change that tend to get the most attention. By the way, these dramatic images that you see come courtesy of federal investments in science that have been made over the years. In this particular case, the MODIS instrument, or actually there are two of them, on board NASA satellites have been sending down images like this for nearly 20 years. And as we're going to hear today, other federal agencies are also collecting observations and developing advanced modeling techniques that improve our understanding of climate change. These investments not only contribute to the scientific understanding of the world, they serve a valuable role in helping the private sector understand and prepare for climate risks. If you're interested in learning more about how businesses are using climate data, I'll just encourage you to tune in to another C2AS webinar that we're hosting on Monday, that's October 2nd, and we'll be talking there about corporate reporting of climate change risks. So that's a topic that's getting more and more attention from the investment community. We have a great lineup of speakers for that webinar as well, and you can find registration information for that on our website. But now let's tune to what you actually wanted to hear about today. We'll start first with Alan McCray, who's going to tell us about weather and climate observations and the information services that are provided at NOAA. Alan, I'll pass it over to you.
Thanks, Ashley, so much. I think we can go right ahead and start on the first slide. I do offer my contact information again at the end. So actually, Ashley, thank you for teeing that up so well between the wildfires, hurricanes, and floods. We do have a rising demand for climate information and the experience that folks are having as they come face to face with both the extreme events and long-term changes that people are experiencing already. These changes are happening across lots of different sectors, as I have listed here, and you'll hear more deeply about the energy sector and how the information is servicing them, but we also try to do our best to apply the data from NOAA to a lot of these different sectors, including the ones that we regulate, like marine ecosystems and living marine resources, but also those that we support at the state level with coast and coastal resiliency, and the work that we do around both too much and too little water. I guess maybe these are timed. Are they timed, Ashley? Oh.
No, sorry, that was human error. Please go on.
Okay. So lots of different sectors here, some of which rely directly on weather impacts and also long-term changes in the climate that happen over scales of around 30 or more years. So that's a distinction between weather and climate, but we do look at those extremes. So moving into the next slide, this is a real showcase of the kinds of information and data you can receive from NOAA at all different scales. And so I love this slide to show the work that we do across the temporal scales, as I was saying, thinking about the weather time scale of daily to weekly and even out to monthly. And then we cross into kind of the climate time scale as we move into seasonal, interannual, and decadal and beyond. So that's across the top there. And then the vertical side is looking at it in terms of spatial scales. So we try to apply the information at local scales, regional scales, and national scales. And using this format is how I laid out the rest of the talk, starting first with our national products at the bottom, and then moving into some of our regional information, and then down to the local scale. So I'll just highlight these now in case we don't get specifically to some of these products, but This slide does also get into who uses this information. So we do a snowfall impact index that we use for FEMA in case of winter storms and icing events. That also applies well to the energy sector in terms of icing. We do heating and cooling degree days, again, for the energy sector, but for lots of different reasons. And then going further into temperature and precipitation outlooks at the seasonal scale, we release those at a quarterly basis. And then just also the hurricane tracks. Ashley mentioned, of course, that we have hurricane information as part of what folks have been experiencing, and I'm sure you guys have all been tapping into the National Hurricane Center lately. But we also do a long-term history of the hurricane track, so you can get a sense, at least in the Atlantic. You can get it around the globe, but in the Atlantic, the hurricane tracks show an interesting pattern that sometimes is useful across the timescale. We also do compilation reports at the billion-dollar disaster, so trying to track whether multi-million or billion-dollar disasters are occurring more frequently, and I'll show an example of our extremes index that's used by the insurance companies. So lots and lots of different information, and I'll show you some, we'll dive deep into how to access some of that stuff. So we'll move to the next slide. So starting at the national scale, there's a few resources that have come out in the last few years. First is the National Climate Assessment. We have a mandate within NOAA, but across the government really, in terms of all of our partnerships and responding to the global framework or the global, Global Change Research Act, which is mandated that the national assessment be produced every 4 years. And so as a result of that, this screenshot is actually from NCA 3, which was done a few years ago, and we're actually in the midst of working on NCA 4. So those chapters have been written and are in the process of editing prior to going out for public comment. So I'm happy to say that you guys should take a look at the public comment period, which should begin on November 3rd. The additional piece is the Climate Resilience Toolkit, which is at toolkit.climate.gov. It's a wonderful resource, both in terms of looking at stories, looking at a 5-step process towards resilience that begins with, information and ends and planning and thinking about your vulnerabilities to different pieces of the climate problem, and then getting deeper into the how to take action. So there's a 5-step process that's included there. There are resources listed there by region, and I'm happy to say that we just completed the Northeast region. So there are a lot of resources in there that are cataloged specific to the region that I'm working in. And then the last thing that's really an interesting, cool new thing is the Climate Explorer tool. And so within the Climate Resilience Toolkit, we are now using web mapping services to produce some of these images for download. And so the Climate Resilience Toolkit has this Explorer for using the map-related products. Next slide. So moving deeper into the national access and how do you access all kinds of government collected information. And it's really not just government collected, it's actually all the academics and pretty much everyone that's taking measurements is meant to ultimately land their information within the National Centers for Environmental Information, which I've abbreviated here as NCEI. So within NOAA's satellite service, this was originally formed to download just bazillions of data, and we call it terabytes of information that comes off of the satellite system. This office is also home to a lot of the coastal and ocean data. We're home to the World Ocean Data Set, ocean drilling data that comes from the Global Drilling Program. We also have space weather data coming from solar flares in our space weather program. We have weather balloon data to look at all of the atmospheric measurements of pressure and temperature and stuff all the way up to as high as the balloon goes until it expands so much that it pops. And then we go to hourly precipitation data, and we also have ocean data that are measuring vertical profiles using Argo profiling floats. And we also have paleoclimate data, which gets into tree rings and pollen and ways that we can measure long-term change in climate prior to the observational record. So our observational record at NCEI extends back to 1895, and the paleoclimate record helps bring it way back into geological timescales using all of those methods mentioned, pollen and tree rings and ice cores and others. So that really extends the data record. Next slide. So how do you get at all this stuff? Well, it's terabytes. I forget how many that are being archived at this moment in NCEI. But the access is available through this yellow web URL that I've given you guys. We've redone our website so that it is a lot easier, even in the 7 years I've been working for this part of NOAA, that it's much easier to find a lot of this information. So what's on the menu? Well, as mentioned, there's a lot of terrestrial station data. So those are taken from the weather balloons, but they're also taken by our long-term airport sites. They're taken by observers, just like yourselves and others that may serve as a daily observer for the Weather Service. Those data from your backyard are uploaded using standardized equipment so that we get temperature and precipitation measurements from hundreds of stations across the country. And those help inform the weather forecast on a daily basis and the observational record that goes into the long term. We also have satellite data, and Ashley showed some of those images from the MODIS satellite. All of those data are archived, and it's interesting because if you do time slices through the 20 years that MODIS has been operating, you can get what's called a climate data record, or a long-term slice in time so you can basically create a time series using visualized satellite information. So we've been working on that a lot with some of the sea surface temperature data. And there are other CDRs as well, climate data records. We also have, as I mentioned, the buoy data that in the ocean go take vertical profiles of temperature and salinity and other features of the ocean structure, which help us get a better handle on the ocean heat content and other pieces. I've mentioned the paleoclimate records. And we also have a long-term record of bathymetry, which includes some really high detailed three-dimensional images of the ocean floor, which can be very useful in terms of exploration for oil and gas, but lots of other pieces. So we use that a lot in the research realm as well. So I think I've mentioned a lot of the things on the menu, but I encourage you guys to explore deeply into the access part of NCEI, so that's available at this website. Next slide. So some examples of what I call the most these are pretty highly used pieces of the NCEI record. And one on the left is called Climate at a Glance. And I didn't put the URL on here because it's actually really easy to Google on NOAA Climate at a Glance, and you can pull up this tool. And the easiest way to access these is really the easiest way to access some of the station data. So if you can search on stations that are close to you, or close to your hometown, or close to a place where you're giving a talk, you can search on the maximum temperature at that site. You can search on the average temperature. You can do a drought indice called the Palmer Drought Index to take a look at how drought has impacted that area through time. So the plot below is an example of a search that was conducted using an annual measure. So, an average point in a monthly time frame over the course of several years over the period of record in Boston. And so that shows what, interestingly, most of us know, but it does show in the observed record an increase in temperature through time. And so if we ran a best fit line through there, you would see that temperature increase that we've all been talking about as part of the national assessment and other products from the International Panel on Climate Change. And then on the right-hand side, you'll see the U.S. Extremes Index. This was actually created in large part due to insurance companies and others that were asking for a product that was kind of a synthesis of all of the information that we have on extremes. And so the Extremes Index is compiled from precipitation records. Greater than 1 day precipitation is shown here. But we also have a record of high temperatures, and this is a combination of our drought products, our temperature products, our precipitation products, and we've recently added some of the storm records as well as extreme events that could lead to, essentially, we've decided to produce it as a bar graph to just show that we're seeing changes in the amount of extreme events that we're experiencing, and in this particular case, the amount of greater than 1 inch rain events, greater than 2 inch rain events in a 24-hour period. And so you're seeing that precipitation is indeed shifting across the continental U.S. So you can do this by region, and you can see whether or not precipitation has shifted in your own region. And you can also do it for the country, which is why I show it under some of the national products here. So that, sorry, quickly before, never mind. Go back, Ashley, please. So just quickly in terms of producing this graph, I again showed the graphical interface where you can pick the region that you want to do, you can pick the indice that you want to do, and you can pick the time frame that you want to graph across. So that helps produce that, that plot. So that's just one, those are a couple, I guess, of many examples where you can click on the data that's of interest to you, and then it'll help you produce a graph. So hopefully that's where you've seen some of the graphs in your experiences with climate discussions of late. But if you want to produce your own, that's a good way to go. And then underneath this graph, which I cut off in the plot here, but you'll see the black section on the left-hand side, and that basically brings you to the raw data that's used to produce the plot. So if you just would like to have the raw data, it is available. Next slide. So regional climate services is where I sit, and you'll see my mug in the northeast section, and I cover all the way from Maine down to South Carolina in the green part of the lower right-hand corner. But I don't do that alone. I do it in large coordination with the American Association of State Climatologists. The colors on the map are less important than the fact that almost every state in the union has a state climatologist that's been named either in the state government or in academia. Tennessee is now filled in, and the only one that's missing is Massachusetts in the whole 50 states, not just in the continental U.S. And so the state climatologists really help bring the information that I showed you to the state scale and working with the state customers. But we also do a lot of that in regional climate services, and we do that in partnership with the regional climate centers, which are an academic partner of ours that we've had for about 25 years through grants and contracts. And these guys really help tailor the content of what I've showed you at the national scale down to the regional scale and help bring it to industry supporters as well. So I just want to showcase the kind of the three-legged stool of how we operate in regional climate services. Next slide. So some of the key products at the regional scale include the ones that we do produce, that we co-produce with the state climatologists and the regional climate centers. And some of you may have seen our quarterly product on the left-hand side. It's a compilation of all of the information that we've gathered over the past 3-month period, looking at patterns of low precip or high precip, high temps and low temps, some of the major events that have happened across the country in the last few months, and then we do a look ahead to the next 3 months using the Climate Prediction Center's seasonal outlook. We also host a monthly webinar series in the middle through the Regional Climate Center in the Northeast, and I encourage you to take a look at the URL or just Google on Eastern Region Climate Services under the webinars. And we try to get to the sector information, and that's where I'll go in the next few slides. I think we can skip this one because I talked about the Regional Climate Center, but it does get into the menu on the Regional Climate Center about products that we produce jointly with the Department of Agriculture, as well as products that we have for the transportation sector. So I'll show a little bit more of those in detail. So one is if you're asking yourself about water resources, you can do a map as I've shown you, or a graph as I've shown you, about the patterns of one-day precipitation, or you can do patterns of monthly precipitation. You can show those on a map through our website at the National Centers for Environmental Information, and you can also see them on maps using the Applied Climate Information System that's available through the Regional Climate Center. But the other thing is that we do this in partnership with the U.S. Geological Survey and the extensive stream gauging network that they have shown on the left-hand side. And that's done by downloading a lot of the stream gauging information to the Weather Service to make sure that the Weather Service is able to move the observations that are taken by the USGS to the forecast done by NOAA's river forecast centers. So I encourage you to take a look at the river observation and forecast information that's available, and also the snow data when it gets to be that time when we're more concerned about snow. And also the precipitation frequency, where we've taken a look at the change in precipitation and the increase in precipitation And actually, some states have moved this into the decision frame where they've actually authorized the state to produce legislation around using NOAA's extreme precipitation frequency estimates. So that's Atlas 14. The product is Atlas 14, and it's volume 10 for the Northeast, which was just completed. On the right-hand side, we look at the two little questions. And that looks at the drought monitor, which is a production of the National Drought Mitigation Center, which is located in the center of the country. But it does show the most recent plot where we're experiencing drought conditions in coastal Maine, as well as the mountains of North and South Carolina. So the interesting and exciting part is that the drought early warning system, while it covers most of the West for obvious reasons in that lower continental U.S. map, I'm excited to introduce the new drought early warning system for the Northeast. It's bad that we experienced the drought, but it's good that we've received some attention from the National Integrated Drought Information System to fill in that white space on the map. So moving on to the next slide. Coastal communities, we do a lot in coastal communities through the National Ocean Service and the production of the Digital Coast Atlas. This particular image is part of the sea level rise viewer that's been very popular around the country for its resolution in taking a few scenarios of sea level rise and putting them onto Google Earth images to show, in this case, what Charleston, South Carolina would look like under a 6-foot flood event, and so, or a 6-foot sea level rise scenario, which is well within the realm of possibility. And so it's important to use these maps in the planning phase to think about where to site different parts of your infrastructure. I would be remiss again if I left out some of the other federal products, including the USGS's Coastal Hazards Portal, which takes a deeper dive into the sea level rise question, looking also at the type of sediment that it's impacting, so that if the product is if sea level rise is impacting a bouldered or sandy area, it may filter in a little bit more than it would on a muddy soil substrate. So the USGS looks at that with including the different soil types. Next slide. And we also apply these information to different sectors. So I use the coast as a sector, but in and of itself, they contain a lot of different sectors. But we also look at the health question in partnership with the Centers for Disease Control and their BRACE framework, which is building resilience against against climate effects. That's done at the state scale, and it uses a framework that we've integrated called the National Integrated Heat Health Information System, a play on the NIDIS framework where we were talking about drought. But in this instance, we are mapping some of the changes in heat conditions and looking at heat warnings and people's response to it in terms of emergency room visits as a result of heat. The Weather Service, has actually reduced our heat index thresholds in some instances as a result of some of this climate work on longer scales looking at increasing temperature. Next slide. So just a couple more on the sector application of these data, but I introduce you to the Infrastructure and Climate Network, which is a wonderful partnership between the state departments of transportation officers and officials and academics and government scientists that are working together to produce climate data in a way that's useful to transportation officials, including the map on the right-hand side, which is a freeze-thaw map produced by the Applied Climate Information System at the Regional Climate Center at Cornell in this instance, but we have regional climate centers across the country. So I hope that you'll use their expertise in the West anyway when it comes to fire science. I'm thinking of Brian and the work that Tim Brown does out there with their regional climate center. But this in the East is looking at freeze-thaw indices to help with road closures, where people are driving over roads or determining whether or not to drive over dirt roads. And the state will open and close those dirt roads depending on their ability to freeze solid and enable driving, or their thaw index, which could mean that they're too soft to drive on safely with large, heavy loads. So that is a product that we were using temperature information and spatial data to try to assess, to just give an estimate of where those road closures might occur. Next slide. So this is really the last slide, but I just want to say that the application of the federal climate data is really important, and that's the sole reason that NOAA has invested in the regional climate service directors, myself, and there are meant to be 6 of us across the country. And the support of that program is critical as we try to make real science, real data like we have in the terabyte form, come to life in the sectoral way. And so a lot of these meetings that we hold are really to find better, allow people better access to the information. So I'm really appreciative of you guys being on this call, but they also allow better application of the data to make real world decisions. So I thank you guys for being on board, and I look forward to any further conversations that you'd like to have with us on more details.
Ellen, thanks so much for that overview. There is just a huge wealth of resources available, and to cover it all so quickly is a true challenge. But hopefully people who are listening have learned something new about what information that there is and is publicly available. Now that we have established where you can go to see the climate that we have today, we are going to have some of the experts from Argonne tell us about how we think about the climate of tomorrow. So Tom and Yen, I'll turn it right over to you.
Thanks, Ashley. My name is Tom Wall. I'm a civil engineer with the Risk and Infrastructure Science Center, Argonne National Laboratory. I'm joined by Feng, who's a climate scientist in our Environmental Sciences Division and a frequent collaborator of mine working on climate resilience planning projects. And so we want to I guess, pull back a little bit and give a broader view of climate modeling and specifically climate model downscaling and give a perspective on where a lot of the data and information and resources that Ellen talked about, where that comes from and how it's generated. So Yan's going to start by sort of answering the first part of the sub-question here of how does it work, and then I'll get into a little bit about what does it tell you and some of the questions and the thought process behind this and things that need to be mindful of when getting into the climate resilience planning process.
Next slide, please. So as our awareness increases, considerations of climate changes are being incorporated into many decision-making processes. Unfortunately, as just talked about, we don't have observations of the future. So climate model outputs are used increasingly by industrial sectors, regulatory agencies, and policymakers for future projections and risk management. Climate models are developed as tools to understand how the climate system works for scientific research. For their applications to a broader community, it is important to know how do the climate models work, what do they produce, and whether the model outputs are fit for the intended purposes. Next, please. In brief, climate models are mathematical representations of the climate system based on their fundamental physical laws and our best understanding of the physical processes. Sophisticated models are increasingly able to include more details. The state-of-the-art ones include atmosphere, land, ocean, glaciers, sea ice, rivers, and interactions of these 6 major components. It simulates the evolution of the winds, temperature, humidity, and atmospheric phenomenon by solving mathematical equations using computers. On average, climate models about 500,000 lines of computer code. Next, please. So in global climate models, the atmosphere is divided into 3-dimensional grid system made of several millions of grid cells. In each grid cell, if you can click, that will appear in animation. The equations describing the physical processes are solved repeatedly for successive time steps that go forward in time. Each grid cell has unique solutions of temperature, humidity, rainfall rates, and other fields. Next, please. The number of cells in the grid systems defines the model resolution, or we say granularity. Next. In the last 3 decades, the global model resolution has increased several factors from originally 200 kilometers in the mid-1990s, in which you can see the Florida state has many too large grid cells, to 100 kilometers about 10 years ago, and then to 50 kilometers at present. The next generation climate models will have a grid spacing of 25 kilometers also. Next, please. One of the examples is the Department of Energy exascale and Earth system model that is set to be released next year, which will have a resolution of 25 kilometers on a global scale. Next, please. So global climate models are useful tools to understand the climate system. Are they reliable? Well, they have shown capabilities of reproducing large-scale and decadal trends in observations. For example, I'm showing you here the global mean surface air temperature trend. The thick black line are observational data sets. The observed temperature rise during the last 2 decades before 2005 is consistently predicted by multiple climate models, indicated by the light green lines. It provides necessary evaluations, maybe not sufficient for the model projections of temperature trends in the next 50 years or so, indicated by the colored lines. Next, please. For general public and other sectors, however, it may be more interesting to know the local and near-term climate patterns. For instance, how many heat waves or floodings we're going to experience in the next 5 to 10 years, rather than to know how much the global mean temperature will rise. So those fine-scale features are very challenging for global climate models with their resolutions to capture. The left figure shows the surface temperature predictions in 3 model resolutions. The outermost domain has a resolution of 18 kilometers, similar to that of the highest global climate models. Going toward to the center, the resolution is refined to 2 kilometers in the innermost domain. You can see larger variations in the surface temperatures are predicted with the highest resolution in the innermost domain. For example, over Sierra Nevada, compared to the smoother changes over the mountainous regions in Montana. This could lead to different counts of local hot bays depending on the model resolution. Furthermore, regional downscaling model outputs at higher resolution show better comparison with observations. The 3 panels on the right shows you the differences between the model and observed precipitation events over 3 U.S. regions respectively. The length of the bars indicate the model deviations from the observations. The longer the bars are, the larger errors the corresponding models have. The global climate models indicated by green, yellow, black bars systematically underestimates heavy precipitation events and also have larger errors than downscaling models indicated by other color bars over each region. So increasing resolution by a factor of 2 might lead to 10 times increase of computational costs on a global scale. It is very expensive to do that with global climate models at higher resolution. So therefore, climate model downscaling is an effective way for that purpose. Next, please. Broadly speaking, there are 2 types of downscaling approaches, dynamic versus statistic downscaling. Next, please. Dynamic downscaling translates the global climate model outputs into local scale features by running a regional climate model at higher resolution over a smaller region. The right figure shows rainfall predictions over North America at higher resolution from a regional climate model that uses the global climate model outputs from the left figure and incorporating higher resolution surface data sets such as topography and soil moisture to better capture the physical processes. Dynamic downscaling involves running a physical model, so it will require certain computer resources, although it will be much less than global models. In contrast, next please, the statistic downscaling does not require running physical models. Instead, it uses statistic techniques to derive relationships between large-scale climate patterns from global climate models and local observations, and then use the derived relationships to downscale the global climate model future projections to obtain local scale estimates in future. So it is computational efficient. However, it assumes implicitly that the relationship derived from the historic data training step is always applicable in future climate. This works for some climate characteristics, for example, seasonal temperature patterns, but does not hold for all the climate patterns, especially for extreme events. For example, the occurrences of the heavy rains related to the area mean rainfall rate will evolve as the mean rainfall rate changes. In these cases, dynamic downscaling would provide physically based estimates based on our best understanding of the rainfall processes. So selection of the suitable downscaling products depends on the nature of the problem. Next, please. There are a few climate model downscaling data products available over North America for free downloading. The NARCAP available at 50 kilometers, and the North American Codex program provides data at 25 to 50 kilometers. Both datasets include multiple regional climate model outputs using multiple global climate model outputs as inputs for different future conditions and to give a range of uncertainty of those estimates. NARCAP also includes dynamic downscaling using the global reanalysis data, which has observation ingested as inputs. At Argonne, we have produced the dynamic downscaling products at 12 kilometers over North America for 20 years. That's about nearly 700 terabytes data. And the ongoing work is to generate a higher resolution downscaling climate data at 4 kilometers, as well as hydraulic data sets. So those data sets could be made available upon request. In addition, the IPCC and the ESGF Data Center provide global climate model data products if you're interested. So finally, I would like to conclude with a few questions to think about before use of the climate model data. One has to take in consideration of the time periods of interest, whether it concerns about localized feature or relates to large-scale trends, whether the downscaling products provide reliable statistics for climate patterns of your interests, and how to transform climate data to actionable analytics. So Tom will talk more on these matters next.
Great, thanks, Yan. So next slide, please. So as Yan mentioned, there's a lot of data that's generated from global climate models, from regional climate models, these downscaled products. Ellen's given a great overview of a lot of data that are available and made publicly available online. So I want to step back and sort of cover three broad areas that I think are worth consideration at the outset of climate resilience planning efforts as you pursue climate model information and climate projections that are most actionable or most relevant to the specific context of your business planning or design effort. And as Yan alluded to, these are the time frame of concern for your planning effort, the specific climate variables that most usefully or most actionably inform the current planning effort, and then probably the toughest question, that's what's an acceptable level of uncertainty in the planning effort. So I'll spend a couple slides on each of these questions. Next slide, please. So the first has to do with the planning time frame. I think commonly there's a paradigm in climate model data that's made publicly available that we provide projections for the middle of the century or for the end of the century. But climate models are run for much longer time domains, and there's a lot of data that may be available in research centers or elsewhere that is not immediately available online, but could be available if asked for, or could be made available with minimal additional processing by the researchers. And the key here is to align the climate model data that you're pursuing with the specific planning context for the climate resilience planning effort. So if, for example, you're planning to design and build a new facility, and that facility is, you intend it to have a 50-year design life, there's not commonly data that's made available projecting climate impacts in 2070, which would be relevant to ensure the resilience of that facility over that its design life. But that could be made available or could be available with some additional looking or with pursuing that with the folks who are providing the actual climate data itself. The next has to do with climate data is generally projected in the future for a time range. And so the figure, if we look at the middle figure shown below, it shows average annual maximum temperatures for northern Illinois. And you'll notice that it's projected not just for 2050, but for five years before and after. So to capture the mid-century, we model 2045 to 2054. Next slide, please. And so we can model and get information just for 2050, but climate is variable. It varies from year to year, and if we only look at 1 year in the future, we miss this variability. It's called the interannual variability, and if we model 10 years, we're able to start to begin to define statistical distributions for how climate impacts like precipitation or temperature or other types of climate information may be characterized in the future as different from today. Climate models generally operate on a decadal scale, so that's one of the reasons we look at 10 years to capture information about the midpoint in the case of mid-century for 2050. We could compute longer time frames in the future. We could do, say, 2040 to 2060, but the challenge there becomes computational resources. So it takes a much greater amount of computing time on massive supercomputers or major computing resources to generate that data. So 10 years is somewhat of a sweet spot for trying to balance having enough projected data and information to reasonably characterize variability in the future climate system while not requiring more resources than more computing resources than may be practical. Next slide, please. So the second question has to do with climate variables and what climate variables are most relevant or needed for the specific climate resilience planning context. And there's a lot of information that these climate models, global climate models, regional climate models, can develop and output directly. And this table shows just a sampling of the types of data that can be produced from climate models, from the more common things in the upper left, like precipitation, average air temperature, maximum minimum air temperature, to a whole range of other types of variables. And in some planning contexts, this information may be sufficient. You may just need the information about precipitation at a specific location for a certain time in the future, or information about air temperature. But next slide, please. But some information and some climate impact information requires either additional analysis or additional modeling. So extremes are a good example of this: extreme temperature, extreme precipitation. Remember, if we're modeling for 10 years in the future and we're concerned about an extreme event, something like the 100-year precipitation event or the 50-year precipitation event, it's probably not likely that that actually occurred in the 10 years that you modeled in the future. But 10 years allows you to begin to define the statistical distribution of variability from year to year for some of these types of climate impact variables. And these extreme events live at the far edges of these statistical distributions, or at the tails of these distributions. And so with some more advanced statistical analysis, we're able to, and I really admit this is an emerging field of statistics, but we're nonetheless able to begin to reasonably characterize these extreme events by conducting some additional analysis of the data that comes directly from the climate models. Next slide, please. In addition to analyzing the data itself, sometimes to get relevant climate impact information, we have to conduct additional environmental modeling on top of that. And so this is an example of a project we worked on that was focused on coastal inundation of infrastructure as a result of hurricane storm surge flooding on top of sea level rise. So how does a greater base of water, as may occur from sea level rise, how does that exacerbate or amplify the coastal storm surge flooding associated with a hurricane? And so we can take sea level rise projections and put that into a coastal storm surge model. And the figure on the left is one of the outputs from that. It's geospatial in nature. We can then look at projected water depths and better understand some of the inland flooding in that area. And then the figure on the right takes that information and then, in this case in Google Earth, overlays that with information about infrastructure locations. So we can then begin to characterize the vulnerability or the risk of that coastal infrastructure. But none of this is possible without taking some of the data that's more directly extracted from the climate models and conducting additional modeling or analysis on top of that. So it's in identifying the climate variables that you need for your planning effort, it's beneficial to be mindful that some of it can come directly from the climate model, some of it requires additional modeling or analysis. Next slide, please. The last question, I think, is, as I said earlier, arguably one of the more challenging questions, and that is, what is an acceptable level of uncertainty in climate projections? Do you plan for the best case scenario? Do you plan for the worst case scenario, or really somewhere in between? And I think it's helpful to understand a little bit of the sources of uncertainty in climate modeling. And one of the big ones that is at the very beginning of the climate modeling process has to do with the emission scenarios used to drive the climate models. So emission scenarios refer to plausible conceptualizations of how greenhouse gases may be concentrated in the atmosphere in the future. There was an older family of emission scenarios called the SRES scenarios, or Special Report on Emission Scenarios, things like the A2 scenario, the B1 scenario, things that you may have heard of in your work in this area. Increasingly, we're moving towards the newer family of emission scenarios called representative concentration pathways, or the RCPs, and that's shown in the right-hand figure. RCP 8.5 is a less optimistic view of the future, I guess, that assumes more business as usual with respect to various social and economic factors and renewable energies and things like that, and essentially assumes or postulates in the future greater concentrations of greenhouse gases in the atmosphere, and therefore greater extent of climate change, or greater magnitude of climate change. RCP 2.6 is a more optimistic view with greater market penetration of renewable energy and various other social and economic factors, and therefore less climate change or less extreme amounts of climate change in the future. And then RCP 4.5 and 6.0 fall somewhere in the middle of those. But nonetheless, they begin to characterize the range of uncertainty for how future climate may occur, and these form the foundation for a lot of the climate modeling, both globally and regionally, that Jan spoke about earlier. There are other sources of uncertainty in climate modeling, certainly internal variability within the models, regional biases in some of the models that may affect more near-term projections, but nonetheless, this I think gives a good perspective on we can begin to provide bounds for the range of uncertainty in climate modeling. Next slide, please. And there are ways to begin to account for these ranges of uncertainty in our modeling efforts, and therefore in the information that's provided to decision makers for planning, engineering, or other types of activities. So this is an example of an effort that we worked on that was focused on watershed flooding and river flooding in the Northeast, in Southwest Maine. It also provides a good example of how we can't just take climate data directly from the models. If we want to look at flooding, we have to conduct additional modeling on top of that data to better understand how precipitation manifests in a watershed as surface water runoff and therefore flooding. But it starts with, in this example, taking several projections of extreme precipitation over the region, and that's what the picture on the left shows, one of these scenarios. Taking that information and putting it into a hydrologic model of a watershed, and then a hydraulic model of a river, and producing, through that modeling, producing what's called an IDF curve, or an intensity, duration, and frequency curve. And it's just simply a tool that engineers and water resource managers use to represent the intensity of a flood. So if I had precipitation of a certain intensity for a certain duration, was that a 20-year event, a 50-year event, a 100-year event, or so on? And what the figure in the bottom right is showing, that under historical context, the yellow line represents flooding in the Presumpscot River in this case. The orange line is the median value for stream flow in that river, and then the gray and blue lines form the upper bound and the lower bounds that were generated by looking at multiple different climate scenarios in the future, and therefore precipitation data projected for the future. And I think that we'd of course love to see the upper bound and the lower bound of uncertainty closer to the median value, but nonetheless it begins to quantify the uncertainty associated with these stream flow projections. And also in all cases, it does show that in the future, peak stream flows in this river will be greater than what we've seen under historical context. And by beginning to quantify this uncertainty, we can start to plan around that. And there's a fairly robust body of work about decision making under uncertainty. I've provided one citation here that I think is it's a few years old, but it's useful in that it provides a broad overview of maybe 24 different methods for decision making under uncertainty in the specific context of climate change, things like scenario analysis or robust decision making, and provide the path forward for dealing with uncertainty in the decision making process and not letting that prevent progress in climate resilience planning. So next slide, please. So this will be my last slide as well. The three questions that I think, just summarizing, are useful to bear in mind when setting out on to conduct resilience, climate resilience planning or climate adaptation planning. What's the time frame of concern? What climate variables specifically do I need? What's an acceptable level of uncertainty? I would encourage anybody who is just getting into climate resilience planning or is continuing to do so in their work to seek partnerships. This is not something that should be done alone. Ellen mentioned state climatologists. I think that that's a great resource. Finding those people with local expertise on climatology in your region, working with local universities, many of whom are engaged in climate science and climate modeling or environmental modeling of watersheds and other things. National laboratories, we at Argonne do a lot of regionally downscaled climate modeling, but other national laboratories are also engaged, actively engaged in climate modeling and have their own areas of domain expertise and may prove to be useful resources. Regional government offices, again, a plug for Ellen and the work that NOAA is doing. They know where the data is. And to borrow a term from Linda Mearns with the National Center for Atmospheric Research in Colorado, I was on a webinar a couple of years ago, and she was talking about the need for climate interpreters and people to sort of act as an intermediary between you all, the end users of this information, and those of us who are generating this data and making it available. These people who you can work with in partnership know what data is available. They know where to find it. They can help answer the question of is it better to use it dynamically downscaled data or statistically downscaled data in my application, and can help you begin to answer some of these key questions about time frame, which variables, and how to deal with uncertainty that can help you sort of move towards actionable information and as you engage in climate resilience planning. So thank you all, and thanks Ashley for organizing the webinar, and looking forward to answering some questions here after Brian.
Thank you so much. Yeah, we've heard so much about the data that's out there, and I think everyone who has spoken so far has talked about how these are not just academic exercises going on. Yes, there's a lot of scientific advancement that's happening because of the observational data and advances in the computing power, but we've heard businesses and investments mentioned several times along the way, and the energy sector in particular, which happens a lot because of the very long-lived assets that are common in that sector. So to hear more from that perspective, we have Brian D'Agostino with us from the Southern California utility SDG&E, who's going to talk from the energy sector's perspective about how this data helps inform business decisions that the company is making. Brian, I'll pass it to you.
Well, thank you so much, and good day to everybody. And listening to that last talk wrap up, I really find I am the climate interpreter for San Diego Gas and Electric. I am a meteorologist, and we do support a lot of the meteorological operations here within the organization, and for us that does include integrating climate information, not only in terms of long-term planning, but our ability to anticipate significant and more and more extreme weather events as they impact the utility. So we need to understand it and be able to see them coming. You know, we also just heard about the value of the collaborations. I couldn't agree with that more from our perspective. And just a couple ones that I want to point out here. You know, partnering with our local National Weather Service has been really big, and becoming a storm-ready organization is a big part of our preparedness. Also, being a weather-ready nation ambassador, you know, through the program with NOAA, and then the collaborations with the Energy Commission and also Department of Energy, along with lots of regional climate groups. Certainly a big part. But as we switch slides and head into the first one, what I'm going to talk specifically about here is a project that we're working on as part of California's 4th climate assessment, where we're really beginning to integrate some of this downscaled climate data and make some decisions with it and do some analysis within the utility. So ultimately, we have 2 separate projects. One is looking at electric sector vulnerability to sea level rise and coastal flooding. And then a second project is looking at vulnerabilities to the natural gas system, and that's not just looking at sea level rise, that's looking at all climate impacts. So it's been a multiple year project, but out of these 2 separate pieces, we're really treating it as one project, which is bringing a lot of really good information into our utility operations. The next slide begins to give us a bit of a layout of the approach that we've taken. A big part of step 1 was making sure that we had a good launching point for this project. So started with a really comprehensive kind of literature review, understand what's been done and what is out there. And then we get into the next part, which is really figuring out, you know, which climate data and which downscaled data are we using. Now, an important part of this was collaborating statewide with our neighbors and our friends and our regulators and everybody else, so that everybody has a good understanding of what are some of our standards here in California. You know, we don't want to be looking at a 2-meter sea level rise over the next 6 months, because we've talked about this huge variability. A lot of what it is coordinating on a local, a regional, and a statewide basis, so that we're all using similar scenarios. And that's really happening because we're converging on tools such as CalAdapt, which is a big one that we're using here in California. But then ultimately, the teams we work with, in this case ICF International, is then overlaying all of these risks onto our infrastructure. And that's something I'll talk about here a bit more coming up here in the next few slides. In terms of the risk analysis, this is the part where we're really diving into now. And this is where we start integrating the different areas around the utility and start kind of spreading the word, educating people about what the threats are, and start to come up with possible adaptation options. So the next slide, if we could head on, it gets into a little bit more detail in terms of the tasks that we're taking. So I talked about this kind of briefly in the last slide. But as we get into kind of that final piece, I want to talk a little bit more of identification and evaluation of the adaptation measures. The point I want to make here is that there's so much to learn from our fellow utilities across the country, you know, because many folks down in Florida Power and Light, of course, you know, have dealt with plenty of storms recently. As we head up to the Northeast, Con Ed, up there in New York, and some of the great utilities in the Northeast U.S. dealing with, you know, major storms, coastal storms, including Sandy. Then you get to, I mean, here in the West, in our experience with wildfires, and then the extreme droughts that California has experienced. I mean, there's a lot to learn from other parts of the country, and that's just a point I wanted to make here on this particular slide. Moving forward, what we find is I wanted to give an example of some of the organizations that were represented in a kind of the workshop where we were sharing this information. And then this is a sample map on the right of the coastline here in southern San Diego County. Those little dots that you see on the map indicate where there are coastal substations. And then we can start to simulate, a major storm or a 1-in-100-year storm on top of a certain amount of sea level rise, and we can start to understand which coastal infrastructure could be threatened in the future and start to get a sense of when that would happen. And then we share this information with certain organizations in the company, and it really is. We find that climate could impact many groups. Here, this is listing just a few, but grid modernization, enterprise risk management, emergency management, which is my parent organization that I'm a part of, electric transmission and distribution engineering, construction services. This has large impacts on insurance and risk advisory. So these are the types of organizations that are starting to see the results of this analysis and start to understand how climate change can impact their particular organizations within a utility. But then we also, on the next slide, talk about a natural gas workshop that we looked at. And we have, a lot of the same organizations on the gas side of the utility that deal with this, but you get into, of course, gas engineering, pipeline integrity. These are other important groups. And I wanted to talk briefly about these two images that you see there on the right. The one in the upper right is actually showing landslide projections. So that has an impact on an underground gas system. And with the change in rainfall patterns, there's an increased vulnerability for landslides in some areas. I mean, I think we all remember how intense some of the rainfall in the atmospheric rivers were across California this last year. And those have big impacts. And then also in the bottom right, what we're looking at is our wildland vegetation in that shaded color, and then some of the infrastructure there, as you see the line. So where we could start to see impacts of a changing wildfire footprint on some of our infrastructure. So all very important things to understand and ways that we're using this climate information moving forward. Excuse me. The next slide, I wanted to create some context around, as all of this information was presented to the utility, how it was organized kind of for these different groups. And we found that we really had two distinct groups that we broke this up into. One was, engineering and operation. I mean, design of the system, when could you see water in certain areas at certain times and other things. But then there's that whole other side of enterprise risk and quantifying the risk associated with it, and then insurance and risk advisory. So we found ourselves in two different kind of buckets talking about the same thing. But in both cases, really asking around the utility to figure out what are your initial reactions and why, what kind of problems will this cause us in the future, and what are those key problems? And then let's start thinking about the types of infrastructure that are vulnerable. And we really would go through this discussion on a hazard-by-hazard basis. So this was a very productive kind of workshop that has been held within the utility. And again, coming back to leveraging some of that climate information and climate projections here in a real-world decision-making setting. Moving forward in the presentation. When we start thinking about this, the interdependencies are very important, meaning in a connected grid, in a connected natural gas system, we could be completely resilient within our organization, but we have to think outside of just our system and start looking at our interdependencies with other, our neighbors, but then also there are interdependencies within the utility in terms of, natural gas use is tied directly to electricity demand, and really starting to think about that. and how these two are connected and how they are dependent upon each other. So looking at regional supply, power system interdependencies, and then also downstream impacts and, how some of these vulnerabilities could affect customers and the local economy, and, how can we really think about this in a way that we can mitigate any impact on customers and the local economy as we move into the future is really our priority, and it's how we're thinking of this. Next slide, please. So really the next step that we're going to convene on, and this is scheduled just for a couple weeks from now. We're very excited about it. We're getting all of these folks back together, and we're really going to look at what are some of the best adaptation measures that have been taken, across the United States and across the world. And then it comes into implementing those into our operations. And that's something that we've already started to do. I lay some of that out here on the next slide. And we call it, in a sense, it's a bit of our lessons learned as we head into this. But it really gives examples of how we're leveraging some of this data today. And can you kick forward to the next slide, please? Thank you. I have a couple examples of how we've used the downscaled climate data. And one is the design of a new compressor station that is being built. It's a major project up in the deserts of the high desert of Southern California. And you have to understand, this is a 30 to 50-year asset. And as you build it, there are design standards for temperature and some other environmental components. And, traditionally, you would use average temperature, but, now we look at climate models to say, what do we actually have to build this system to as we develop it into the future. Another one that we've looked at is design standards of the system. As a pole is rebuilt, what is kind of in the company standards in terms of, the highest ambient temperature this could ever reach, because these are all taken into the structural design calculations for the company. So we can go in and modify all of these ambient temperatures in different areas to accommodate this. And then the last thing that we've looked at, when we start looking at long-term system resilience and system hardening, we're always looking at future projects to make sure that the grid stays stable. And now we're looking at climate information in terms of possible routes that transmission lines could take in the future and other things. So certainly a good example of integrating some of this climate information kind of into the core business and the day-to-day of a California utility here. I think with that, I think the next slide goes to questions, I believe. Oh, no, good. I got one more that it just continues. We cannot emphasize enough. I know you heard it towards the conclusion of the last presenter, but mine as well. The collaborations are huge, really a major part of what we do and how we do it. And then the high-level support within the organization, something that is very helpful as well. So in the interest of time, I think I'll leave it at that and hand it back to Ashley. Thank you.
Thank you so much, and thanks to everyone for the presentations. Thanks to all of you who are listening and are sending in your questions. We do have quite a few that have come in, but in case you have a question on your mind and haven't typed it in, I'll just remind you that you can ask a question by entering the question into the box. We have too many people on the line today to unmute lines, so I'll just read questions as they come in and ask them of the panelists. And I'll start with one for Ellen with NOAA. Ellen, a few people came in with questions asking for some clarification about what you do with the regional climate centers and what the Regional Integrated Sciences and Assessments, the RISA program, does. Can you speak to that?
Sure, Ashley, and thank you guys for the question. I have a slide on this that talks about the movement of climate information. And I'll use an energy analysis or an energy analogy, and that is the energy being generated, transmitted, transformed, and translated. And so there are basically 4 steps of climate science and climate science information. And there's the generation of that information, which is done in part from our researchers as well as researchers around the country. And those data are included. And so the Regional Integrated Sciences and Assessments Group, the RISA group, is housed under NOAA Research. And so its primary function is actually as a research arm. It may be some social science research, and it does incorporate social science research, but it in large part is looking at the climate science. And then there's the there's the transmission of that information to National Centers for Environmental Information as an archive. But then there's the transformation of that information into usable products. And so that's really sort of the new space of research, as everybody tries to make sure that the research that's done is not for lack of a user. And so there's the operational service delivery that's done through the regional climate centers, and that is on a regular schedule, on a regular basis. We're producing products that are using that information and putting it out as maps and reports and that sort of thing, so that folks are doing that in a timely manner. So that's, I guess, the difference between RISAs and the regional climate centers. We also have the climate science centers from the Department of Interior. So I guess I could get more broadly into a lot of the different providers. But again, those are primarily for research. And so I think the distinction is the primary function of research versus the operational service delivery. And also, I'll call people's attention to the NOAA regional, or the NOAA Climate Services model, which was proposed back in like 2006 or 7 to take a look at the conglomeration of all of NOAA's academic partnerships. So RISA is, again, they are not NOAA.gov employees. They are grant awards that go to academic researchers. And the regional climate centers are as well. And so NOAA was interested in combining the work of the Weather Service and the work of the climate information and climate data into a regional presence, where we pulled information from the RISAs, the regional climate centers, interface well with the Department of Interior centers, the USDA centers, and others, to get a broad sense of how the primary source of information at NOAA is being used by different sectors. So hopefully that answers the question.
Yeah, thanks for that. And maybe the answer is that whatever data your heart desires, you can find it somewhere in the world of NOAA. A question also about the forecasting and the projections and how the climate models work. Tom and Yan, you both told us a bit about some of the inherent uncertainties in the climate model projections and some of the techniques that you can use to address those uncertainties. A question about, since these models are built on data and observations in the first place, is there any particular data set that could be useful in helping to narrow some of those uncertainty ranges in the future projections? Or, maybe more generally, what is it that's driving this uncertainty, and what would we hope that the research can achieve over the next 5 or 10 years to reduce the uncertainty?
That's a great question. This is Yan, so I will take this one. I think, as Tom alluded a little bit in his talk, there are 3 types of uncertainties contribute to the climate model predictions. For the medium term or long-term projections, the model deficiency, meaning that the equations that we are using to solve and simulate the climate is one of the major contributors to the uncertainties in the medium to long term, and also the scenarios, what kind of emissions that we're putting into the future climate model predictions. That's another uncertainty that contributes to the long-term projections. For the near term, uncertainties are mainly driven from the initial start of the climate model simulations. And that is where we need a lot of observational data sets to nudge the model in the first 10 or 20 years time frame to get a better predictions. So in the near term, the observational data sets are highly required, demanding to get the better predictions. In terms of detailed data sets that what we can use, for example, temperature, wind, water vapor, those things have been constantly collected and ingested to the either weather forecast or climate model simulations. And to take that further step, we can also use observations from satellites for like clouds, precipitation, if that becomes readily available. And those things can also be ingested to the model to constrain the simulations. And in another perspective of like land surface data, such as the topography and soil moisture, we can also use those to constrain the boundary conditions, meaning the land and atmosphere interface, and that will give us a better simulations of the atmosphere as well. So, but I would like to address one point though. Climate models are basically based on mathematical equations. Those are derived from the fundamental laws, such as the first laws of motion and the first laws of thermodynamics. So they're not purely built on data, but data can certainly improve the model performance. I hope that addressed the question.
Yes, thank you very much, and a good reminder about clarifying the role of the observations and the theory and how they play together. Brian, several questions are coming in for you, looking for insight, I guess also dealing with this question of uncertainty, but recognizing that an electric utility is not going to build, 5 ± 1 new assets, right? You have to make finite decisions, but in a world of climate uncertainty. So some people want to know a better insight into how you incorporate that model uncertainty in your planning. Do you just toss a range of projections to your engineers and let them figure it out? Do you make a strategic decision at the beginning about whether you're planning for worst case, best case? Can you share some insights along those lines with us?
Yeah, so a big part of that in our case is, electric infrastructure tends to have a life expectancy of 30 to 50 years in most cases. So one of the things that helps us with the range of uncertainty is that we're not planning, our assets don't have lifespans all the way out to 2100, which would make it a lot more difficult because it's really after 2050 that you see the huge range start to develop in a lot of cases. So a lot of what we are using is worst case scenario out to about the 2050 to 2060 range in most cases as we start to look at this. So I know that's kind of a quick and simple answer, but when we start looking at, giving information to our engineers, we go into CalAdapt guidance, and because that's been developed, on a statewide basis through the California Energy Commission with some of the latest science, a lot of times we do use 8.5 as an emissions scenario moving forward, but that is how we have, that's how we've dealt with it thus far.
Great, thanks for that. And one more question about using some of the climate projections in, maybe you'd call it an integrated way, feeding this into other models that look at demographic change and other societal impacts, trying to get at an understanding of how the physical impacts of climate change are going to affect population and communities, what are going to be the social justice and environmental justice of these kinds of coupling effects. Is there anyone who can speak to that? I know that we heard a little bit about overlaying compounding variables, so what happens if you get sea level rise and hurricanes at the same time. Brian, I don't know if you are using your climate model projections coupled with changes in populations over time in planning, for example. Maybe Ellen, do you want to speak to that, and then Brian?
Sure. Ashley, I'll alert folks to a new product we call Convergence. and let me see if I can find it. But the convergence is hosted by the Southeast Regional Climate Center in conjunction with folks in the state of North Carolina. They helped map the emergency room visits with health and tried to look at some of the vulnerabilities, and actually started speaking to the environmental justice issues as part of the Southeast Regional report that'll go into the national assessment. So convergence can be found at sercc.com/convergence. But it talks about climate and health vulnerabilities. It speaks to the partnership that we had with the Centers for Disease Control. But it's really a great tool. Folks were wondering questions like, when do you cancel football practice because it's too hot? When should Camp Lejeune be thinking about not bringing their troops out for training when it's blistering hot? So it was looking at the physical impacts and the population and basing it on when folks were going to the hospital for heat-related illness.
Cool, great. And Brian, any thoughts on how you use climate projections in addition to the other long-term forecasting that you're doing?
Yeah, well, part of what it is, a lot of our load projection models go out for the next 10 years. So when we start looking at the impact on our communities and other things, our focus is just to make sure that we have proper projections of future energy use. So that's kind of our particular impact, is just trying to anticipate any stress that there will be, on the electric delivery system or the natural gas delivery system, and make sure that we can remedy those. Just to make sure that if that football practice is in fact canceled, they'll have a cool zone to go to, that is powered and a way to stay cool. So that's kind of how we look at kind of our impact on, taking this information and serving the community just as an energy provider.
Yeah, that's really interesting. Thank you. Maybe I'll ask one last question, and I'll also send this one Ellen's way. I know that I am a fairly active NCEI user. We receive a lot of questions from the people that we talk to looking for the statistic. It was really hot last month. Is this the hottest of all time? Some really simple, straightforward questions to contextualize the weather and climate that we see. Ellen, do you know offhand what is the most popular data product that NOAA has to offer? What is the information that people really like to get from you?
Oh gosh. So I think, well, for starters, thank you. And I think that it's important that folks do look at the statistics to put it in context. In the East, in the Northeast, people saying, it seems like if we didn't have a summer, it was cooler than normal. Well, let's go check that out. And in the Northeast, it was a little bit cooler than normal, but people in DC wouldn't think so. So we do take a look at that on our monthly State of the Climate report. So that's very popular in terms of setting the context. Additionally, I would say our GHCN data, which is, oh my goodness, I'm going to have a hard time with that acronym, but basically that's our daily data that is most popular for doing the plots. And some of the more robust products, including Climate Data Online and the tool that I showed you guys, Climate at a Glance, are ways to access the data in a simple way. So I'd say those are the most highly used to be able to move from the raw data to the graph.
Great, thanks. Yeah, we all need data for what we're doing. We've run out of time today. I do want to thank everyone for joining us, and for those who are interested in sharing this event with colleagues or for reviewing what you've heard, we are going to be posting the video and audio recording with slides to the C2AS website. You ought to be able to find that in the next day or two. So thank you everyone for your time and attention. An extra special thanks again to our presenters for sharing their insights and knowledge with us today, and have a great day everyone. Bye-bye.